Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue forward with derivatives of trigonometric functions. You should have already watched my video on the two lemmas that we needed to prove some of the stuff involving derivatives of trigonometric functions. You should have also watched the video on how to use those within examples. And finally, you should have seen the video on the theorem and proof of that theorem for derivatives of trig functions. So in this video, we are just going to compute, and I will not rewrite the derivatives. You should have them written down next to you, ready to go. So let's jump into this. All right, this example right here, we just are asked to differentiate. Now, if you're one of my students and you're working on the online homework that I assign, or if I don't assign online homework this semester, then you're working on hand-in homework. You know of a theorem that I actually have you sort of prove in a homework. And that theorem is, if you have a combination of functions, f, g, and h, and you take their derivative, it'll be the derivative of the first times the second and the third, plus the first times the derivative of the second times the third, plus the first times the second times the derivative of the third. So this is an extremely useful theorem. That way, when I have products like this of three different types of functions, I could just quickly compute the derivative. It is the product rule, by the way. If there were only two functions, f and g, it'd be f prime g plus fg prime. But when you have three functions, it just expands to be more inclusive, right? And so you get something like this. If you have four functions, same thing. So let's go ahead and compute that. F prime of x is going to be the derivative of x. Normally, I wouldn't have you write out all this stuff. I'm just slowly going through, right? Times e to the x times cosine of x plus x times the derivative of e to the x times the cosine of x. And then finally, plus x e to the x times the derivative of the cosine of x. Let's take these derivatives. The derivative of x is 1. So this is e to the x times cosine of x. The derivative of e to the x is, well, just e to the x. So that's x e to the x cosine of x. And finally, the derivative of the cosine, that's the trig one. And remember, it's a cofunction. Derivatives of cofunctions are going to be negative. So negative x e to the x. And then the cosine's derivative would be that sine, of course, with the negative. Now, this is almost done, but I would probably take out a common factor of e to the x. It's not necessary, but it's highly recommended, mainly because you might have to compute with this, and it's easier to compute with this when you have it completely factored out. So I'm just going to do this really quickly. Minus x sine of x. Nothing else I really can do there, so I'll leave it as that. Very nice problem, actually. All right, let's differentiate this function. G of x is equal to 1 over the sine of x plus tangent of x. So I often, if not always, tell my students, trig or algebra before trig, trig before calculus, basically. There is a little trig you could possibly do here, but it actually makes the derivative more challenging. You could technically multiply both numerator and denominator of this by cosine. If you do that, though, you'll end up with a cosine over cosine sine plus sine. And that's actually a lot uglier. I wouldn't want to do that. So I would refuse that. And I would just take the derivative as written. So g prime of x is equal to, it's a quotient. So I'm going to use the quotient rule. The derivative of the numerator times the denominator, sine of x plus tangent of x minus the numerator times the derivative of the denominator. So I'll just say sine of x plus tangent of x prime. We'll take that derivative after we're done writing everything out. And then it's all over that denominator squared, all over the sine of x plus the tangent of x being squared. Derivative of 1, that's 0. So this first term just disappears. So we get equals a negative, some stuff on top. Remember to keep that bracket on there because that negative will distribute through the bracket. The derivative of a summation, remember this rule, if you have a sum of functions, you take their derivative. It's the same thing as the sum of their derivatives. That is not the case. I'm just going to constantly remind you of this. That is not the case with a product. You cannot do that. Okay, so, but with summations, you totally can. So here we go. We have a summation. Derivative of the sine is the cosine. I'll just write that in. Plus the derivative of the tangent is the secant squared. And again, I'm assuming that you wrote down all the derivatives from the proof video, so I'm not going to rewrite them here. So derivative of the tangent is secant squared. And then this is all over that sine of x plus tangent of x and quantity squared. Okay, so inevitably, somebody will ask the question, can this be simplified? I don't know if simplified would be the right word. Could it be rewritten? Sure. Simplified? Maybe not. If you want to check to see if it simplifies, you're more than welcome to. Off to the side, I'll just write it in what I consider to be a very shorthand notation. I'll use C for cosine and S for sine, and I'm going to write everything in terms of sines and cosines. So this would be cosine plus 1 over cosine squared divided by the quantity sine plus sine over cosine. And again, that quantity is being squared. And you could see, if you write it that way, that we have what's called a complex fraction or compound fraction, however you want to call it. So I would multiply both numerator and denominator by cosine squared. And if you distribute that into the numerator, you get the following. Negative cosine cubed plus 1. Already I don't like it. And downstairs, actually, I just want to write this out kind of slowly. I can bring this cosine into that binomial there and write it like this. Right? Because that's the same thing. It's sine plus sine over cosine being squared times a cosine being squared. And so what I could do now is I could distribute that cosine through, and you would get a negative cosine cubed plus 1 upstairs. And downstairs, you would have a cosine sine plus sine, all being squared. And that actually does simplify now that I'm looking at it. This is negative. That's a sum of cubes upstairs. So that's a cosine plus 1. I don't know why that does that. It's a cosine plus 1 times a cosine squared minus cosine plus 1 all over. Downstairs, I will factor out a sine squared. I'm left with a cosine plus 1 being squared. And of course, cosine plus 1s can cancel. And so you get this negative cosine squared minus cosine plus 1 all over sine squared times cosine plus 1. And I have to be honest with you, that is no better than what we just have over in black. So end result here is that you have to be willing to kind of look ahead a little bit. So when I looked at this and I knew it's not a good idea to try to simplify this fraction right here, the reason why I made that decision is when I saw I'd have to multiply top and bottom by cosine squared, I'd get a cosine cube plus 1 upstairs. And just to me, that's a very dangerous binomial to try to work with when you have other stuff downstairs. So you're more than welcome to have gone this route. It's the same answer. It's just, personally, I wouldn't have done it. So, yeah, I would probably leave it like this. That being said, with trigonometric functions, you should always try to investigate. It's just worthwhile, especially on a homework. You have a few minutes on a homework, right? You're doing homework that maybe is due, let's say 3 or 4 days later. So it might be a good idea for you to spend the extra little bit of effort to remind yourself of all the trigonometric identities and the algebra in the background to simplify a statement like this. It is part of your job as a student. Now, on an exam, it might be a completely different story. If it was an exam, I would get to this point and I'd say, okay, I'll come back to that if I have time. This is good though, right? So I get to a point and I just say, great, let me move on. If I have time at the end, I'll come back and I'll see if I can clean that up. That's a piece of advice from an instructor. All right, that being said, let's go ahead and differentiate this function. Now, this is a case where I definitely would do a little bit of trigonometry before starting, because a cotangent over a cosine is begging to be worked upon. So cotangent, remember, is cosine theta over sine theta. And also in that denominator is a cosine of theta, because you're dividing by it. So plus e to the theta secant of theta. This just allows me to really simplify the statement. And what I've seen people do in the past is they leave that as a 1 over sine. Don't. It's a cosecant. People will often leave that as a 1 over sine because they just want to use the quotient rule, but I don't think it's a great idea. I think just leave it like this. This is good. Trade it out for a cosecant because we know the derivative of a cosecant. Otherwise, h prime of theta. Well, that would be the derivative of the cosecant of theta plus the derivative of e to the theta secant of theta. One of those derivatives is fast. That would be the first one. The second derivative is a product rule. And instead of taking my time with it, I will just say derivative of the cosecant is a negative cosecant of theta, cotangent of theta, plus derivative of e to the theta is e to the theta secant of theta, plus e to the theta times the derivative of secant, which is a secant theta tangent theta. When I get to the very end here, I look through each of those terms to see if they have anything in common. They don't, so I don't bother factoring anything out. Now you might say, but wait, what if I write in terms of sines and cosines? Won't they have something in common? No, they actually won't. So you don't have to worry about that either. So that's the derivative of that h of theta. Honestly, once you start working with trigonometric functions and their derivatives, they're all very rote, very fast. So it's hard to make any lengthy lecture video out of something like this. But I do like to investigate some other unique details about these functions. So let's go ahead and use Desmos to graph this function g of x equals tangent of x minus 2 sine of x. Let's do that first. All right, so you can see I actually did just graph it. This is the tangent of x minus 2 sine of x. I don't have the function visible to you on the left-hand side of the screen because I want to showcase something here. We were asked to graph this in a window going from x equals negative pi over 2 to 4 pi. So to do that, I just clicked on that little tool icon and I just have a negative pi for pi over 2. And I want x to go all the way up to 4 times pi. And the y-axis, I want that to go from a negative 5 to 5, according to the instructions I was given. So this is a graph of that function over that interval. And that's a pretty good looking function, actually kind of neat. Now that we're done with that, let's see what else we're being asked to do. Compute g prime of 0 and g prime of pi and g prime of 2 pi. Well, that just means compute g prime first. So I'm going to go off to the right hand side here in blue. I'll say g prime of x is equal to, well, the derivative of the tangent is the secant squared, and minus 2 times the derivative of the sine is the cosine of x. And now I can go ahead and compute g prime at 0. If you plug 0 into the secant, it'll be 1. So 1 squared is 1. And then minus 2 times the cosine of 0. Cosine of 0 is also 1. So it's 1 minus 2, or negative 1. G prime at pi, well, secant squared at pi. Secant at pi is actually a negative 1, but when you square it, it becomes a positive 1. And then minus twice, actually I should just write that down. Minus twice the cosine of pi is a negative 1. I write that stuff down because it's a lot for my brain to remember, so this is just going to be a 3. And finally, g prime at 2 pi. Well, this is going to be a no-brainer because trig functions are all 2 pi periodic. Well, not all of them, but they all repeat themselves every 2 pi. So this is going to be a negative 1. You can double check though. Secant squared of 2 pi, that'll be 1. Minus 2 times cosine of 2 pi, that'll be a 1. So there you go. All right. That being said, let's see. Find the equations of the tangent lines to this curve at those 3 points. Great. So this is almost like well, it actually is kind of a synthesis question that we would do normally in a separate video, but I'm just including it in the standard lecture here. So remember, for the equation of a line, you need a point and a slope. Now, we were given 3 x values, 0, pi, and 2 pi. And we computed the slopes at those points, -1, 3, and -1. I just need the y values at those points, but luckily, the y value is whatever the function value is. In fact, just to really drive that point home, I'm going to say the point is is 0, comma g at 0. And this is pi, comma g at pi. And this is 2 pi, comma g at 2 pi. And obviously, that just means go plug those values into the original function. Tangent of 0 and sine of 0 are both 0. So this point will be 0. Tangent of pi and sine of pi are again both 0. So this point will also have a 0 for its y value. This is pi comma 0. And then same thing, g of 2 pi, because everything's 2 pi periodic. There'll be zeros there as well. All right. So we have points, we have slopes, so we can write the equations now. EQNS means equations for me. And so the very first one has an equation of y minus 0 is equal to -1 times x minus 0. Or in other words, y is equal to a negative x. The very second point there at pi comma 0 is y minus 0. Sorry, the equation of the tangent line is y minus 0 is equal to 3 times x minus pi. Well, that's kind of nice. That's y equals 3x minus 3 pi. Still a line, just has a y-intercept of -3 pi. And the very last one, y minus 0 is equal to a -1 x minus 2 pi. And that implies our equation is y equals a -x plus 2 pi. Okay, not too bad, right? So we've done this, this, and this. What else do we need to do? Graph those equations. So let's hop over to Desmos here and graph those equations. All right, so here I am in Desmos. I'm going to go ahead and write in y equals a -x. You can see that is actually a tangent line to that curve at 0, 0. Perfect. And the next one was y equals 3x minus 3 pi. And oh man, that's so tangent that it's hard to see the curve. There you go. Totally a tangent line right there. And finally, y is equal to a -x plus 2 pi. The thing that I want to showcase here and make sure, yes, that's it. Okay. thing I want to showcase here is that these allow you to visualize that you're doing the right thing. What you've done here is correct. All your derivatives are right, your tangent lines are right, all that fun stuff. So this is really a very good looking situation. So we're done with that. And then what happens if you try to find the equation of a tangent line at x equals pi over 2? Well, I don't know. Let's find out. Let's see. Tangent line. Well, I need to get a slope at pi over 2. Let's start there, right? So where's my derivative function? Oh, it's right there. So secant squared technically of pi over 2 and minus twice the cosine at pi over 2. Well, here's the deal. Cosine of pi over 2 is 0, but secant squared at pi over 2, secant doesn't even exist at pi over 2 because secant is 1 over cosine, and at pi over 2 the cosine is 0. So this does not exist. It's undefined. So the whole answer to that question, what happens when you try to find the equation of the tangent line at x equals pi over 2? Well, the issue is that there is no tangent line at x equals pi over 2. Let me write that down. There you go. There is no tangent at x equals pi over 2. Why? Because the derivative doesn't even exist at pi over 2. Well, let's see why that is true. Because the original function doesn't even exist at pi over 2. Tangent at pi over 2 is non-existent. It does not exist. It's undefined. And finally, graphically, just seeing it right here, here's the vertical line, x equals pi over 2. If you zoom out, you can see that's definitely a vertical asymptote. There's no derivative there. All right, so here's the last example. And actually kind of an easy example for a last example, to be honest with you. If your function h is the product of theta and cosine of theta, find the first and second derivatives. We've already kind of done stuff like this, so I don't know why I left this example in here, but we might as well just do it, right? So h prime of theta. Well, it's a product of two functions, so it'll be the derivative of theta. Maybe this is why I did this. Imagine, actually, I think a lot of people, when they see this, they might just say, wait, hold on, I don't know how to take the derivative of theta. You do. H prime of theta is actually the derivative with respect to theta of h. And so I'm taking the derivative with respect to theta of theta times the cosine of theta. And if you're really rigorous and kind of slow with this, that would be the derivative with respect to theta of theta times the cosine of theta plus theta times the derivative with respect to theta of the cosine of theta. I mean, a lot of people probably already know it, but still, d theta is 1. In other words, the derivative of theta with respect to theta is just 1. It's like me saying, what is the derivative with respect to x of x? Well, we know the derivative of x is 1. But that's because we're taking the derivative of x with respect to x. So just be aware, you're taking the derivative of this function with respect to theta. And so it's sort of like this being an x and taking with respect to x. It's the same idea. So this would be 1 times the cosine of theta. Let's see, plus theta. And then the derivative of the cosine is a negative sine of theta. All right. And then the second derivative, which you could write this way if you want to, the second derivative with respect to theta of h. A lot of people don't like that notation. I say a lot of people, a lot of students don't like that notation, but it becomes more powerful, especially in the next section of your textbook, which is the chain rule. It's incredibly important there. So you might as well just get used to it. All right, the derivative of the cosine is a negative sine. And then minus, and I actually would do this in 2 steps here, minus the derivative of theta times sine of theta. And the only reason why I'm taking my time with this is because that stupid minus sign can throw me off. So let's see, we have a minus sine of theta, or a negative sine of theta, minus, and then keep that in a group. Derivative of theta is 1 times the sine, plus theta times the derivative of the sine, which is the cosine. And then I will distribute the negative through. Negative sine minus another sine is a negative 2 sine of theta. And then negative times this is a negative theta cosine of theta. And these types of derivatives actually do occur in Calc 2. So be very aware. All right, I think that closes it out for this lecture video. There'll be another one called synthesis questions up next, where we do some higher level content.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.